I'm Jardine, and today I'll be examining the biophysical interactions of a temperate shelf sea during the winter-spring transition, specifically answering the question, does rainfall initiate stratification? So just a little bit of background first. I'm looking at shelf seas, and shelf seas are coastal seas defined as being under 200 meters deep. And they're incredibly important because they account for up to 30% of the global primary production. Physically, shelf seas are also very important in the sense that they have an annual cycle of being homogeneously well mixed in winter and then thermally stratified during the summer. And by stratified, we mean that the water column is separated into layers based on the different density of the water. So this can be either changed by thermal inputs, such as heat, or freshwater inputs as well. And freshwater inputs from rivers, specifically very close to the coast, do have an effect. They do cause stratification. However, freshwater inputs from rainfall have often been deemed as insignificant, and this is a crucial point to remember throughout the talk. Looking at the biology as well, the phytoplankton are also they're everywhere in shelf seas, and phytoplankton are microscopic algae. And they're plants, so they need light nutrients to survive, and phytoplankton photosynthesis is partly responsible for shelf sea carbon sequestration, so they're really important little guys. And knowing why and when phytoplankton occur is essential for improving the predictive capabilities of global climate change models. So all the data collected for my PhD is done by these autonomous underwater gliders. And gliders are really neat pieces of kit because you can just chuck them off a boat and they stay out in the ocean for up to 3 months, continually profiling up and down the water column, and they just come to the surface and ping all their data. So they're really, really neat pieces of kit. And throughout my PhD, 4 gliders were deployed in the Celtic Sea region of the Northwest European Shelf, between the central Celtic Sea mooring and the shelf break or the CS2 mooring. So these 4 gliders were deployed, and then they were just going between these 2 moorings, continuously measuring as they go. And if we take a transect from all 4 of these gliders, we get a really nice 9-month near-continuous time series between November 2014 and August 2015. And in the top graph, we can see the temperature recorded by the gliders in degrees C. And in the bottom graph as well, this is just to illustrate that the glider is moving spatially at the time. So 0 kilometers is the CCS mooring, that inner part of the shelf. And then the glider is moving continuously between this and the shelf break, going back and forth continuously as it goes. Looking back to the top graph, the way I like to remember this is the shallower bits are closer inshore, so at the CCS mooring, and the more deeper areas are further towards the shelf break. So if we just look at the top graph for now, we can see this annual cycle of a temperate shelf sea. So in the winter, we see it's homogeneously well mixed. So in the black, there's temperature, and in the red is chlorophyll concentrations in milligrams per meter cubed. Chlorophyll concentration being measured, chlorophyll fluorescence is what the glider measures, and we can use that as a proxy for phytoplankton presence and phytoplankton growth. And in the winter, we can see it's homogeneously well mixed. The scales on both temperature and chlorophyll are very, very small, and there's really not that much going on. However, as we get towards spring, you start getting this stratification, this input of temperature into the surface. And at this time of year, the temperature difference is still very small, but it's just enough to split that water column into 2 layers. And this traps the phytoplankton in the upper layer, where they have ample light and ample nutrients, and they form a spring phytoplankton bloom. And this is ubiquitous throughout the northern Atlantic, particularly in the temperate shelf seas. But as this thermal stratification starts to increase further towards summer, so now we have a top-to-bottom temperature difference of about 7 or 8 degrees C, the phytoplankton have used up all that nutrients in the surface layer. So they now congregate to the base of what we call the thermocline. This is this boundary between the 2 layers, and form a subsurface chlorophyll maximum. And then during winter winds start to come on, and then they mix everything up again, so we get back to the well-mixed state. So this is a really nice way to show the annual cycle of a temperate shelf sea. But for the purposes of this talk, I'll just be focusing on the winter and the winter to spring bits. Specifically, how do we get from that to that, and what are the biophysical interactions involved? So for this, although I used 4 gliders in my PhD, I'll just be focusing on 1 glider. And this is a really interesting glider because it was only active for 12 days. So it was deployed at the CCS mooring further in shelf. It did 1 complete transect down to the shelf break, and then it only got halfway back up before it had a malfunction and had to be picked up. But regardless of the fact that it was only out for 12 days, it did seem to capture the onset of seasonal stratification. So in these two graphs, we've got the potential density anomaly, which is potential density is the density minus pressure effects, and then potential density anomaly is just the depth mean density. And then we've got chlorophyll fluorescence, so this is this proxy for phytoplankton in the bottom graph. So there we got this one complete transect down to the shelf break, which is the deeper bit, and then halfway back up. So from what we can see here, first, at the beginning bit of the transect, we can see this this daily cycle of heating and cooling. So in the daytime, you get more thermal inputs into the surface, an increase in buoyancy, which lowers the density of the surface layer. But then it's still too cold. So during nighttime, when you get net cooling, everything convects, and we get this well-mixed state again. We do get these pulses of phytoplankton in the surface as well, as they're trapped in their surface layer, but then everything gets mixed out during nighttime. But then something happens on the 25th of March, where we get an extra input of buoyancy in the surface, and this just pushes the system enough so that it outcompetes nighttime convection. And we get sustained stratification lasting about 4 days. And this corresponds very nicely to a phytoplankton bloom during the same time. Then the glider moves into the shelf break regime. Everything gets a bit more energetic. There's a lot more mixing going on, so the signal's a little bit fuzzy. But as we come back on shelf, we can see that it's still stratified, and we still have the same phytoplankton bloom. This glider's moving back into the same bloom. And because this is still stratified here, we can say that we have captured the onset of seasonal stratification. This now will not break down until September, November, or even later than that. So what caused this stratification? Density differences or stratification is controlled by both salinity and temperature. So what is actually causing the lighter density in the surface? So we did some correlative analysis to see temperature salinity control. What we did was is this profile correlated to change salinity or correlating? So the thing we're looking at this graph is if the red line, which is more salinity control, and the blue line temperature is to -1, it's more temperature controlled. So and interestingly, the initial bit of stratification is very much salinity controlled. Temperature controls drop specifically because it's at the night time, so it's very, very cold. But we've got this input of buoyancy in the surface due to fresh water, so it goes back to it. So it is salinity controlled. Then we get to the next day, so we've got more thermal inputs from the daily heating cycle, and we switch back to a temperature-controlled regime. But then as we get to the next night, it's still very cold. The system wants to convect, but there's enough buoyancy left from fresh water in the surface so that we switch back to a salinity-controlled regime. Then we go into the shelf break. It all gets a little bit messy. But then as we come back on shelf to this last bit of stratification, we can see that the controls in stratification are pretty much 50-50, temperature and salinity. So although there is a noticeable switch during this area, although there is a noticeable switch between temperature and salinity controls, for the majority of this initial stratification period, it is controlled by salinity. That is, fresh water being inputted into the system. But where did this fresh water come from? It couldn't be from rivers because we're too far offshore, and as well the time of year is all wrong as well. If we would get riverine input, it would be a lot later in the year. So the only solution is rain, and actually there's a great big rainstorm which falls on the 25th of March, and it fell perfectly over the glider path. So this is the little glider path here, and this is the max bit of rainfall, so I couldn't have planned it better myself, to be honest. So we did a back-of-the-envelope calculation to test the measured salinity change based on the profiles, and compared that to the estimated salinity change based on the amount of rainfall that fell. And although it's not quite a one-to-one relationship, it is pretty close. So this is very that rainfall is responsible for the halo stratification seen on the 25th of March, subsequently acting as a seasonal stratification in the Celtic Sea. So further work from this as well will also look at the models such as Gotham and Nemo to see how rainfall has affected previous years, and to also test whether maybe the rainfall was just a fluke, it just happened at the right time and actually it's quite unusual, and if it's just happened in this area or if it happens at other places around the world as well. But also I'm looking at the biophysical interactions as well, so what happens to the phytoplankton. So I said originally that chlorophyll fluorescence is actually for phytoplankton growth, although it does have its limitations. It is hard to say whether these blooms are down to active growth or if it's just a redistribution of all this fluorescence being pushed into the surface layer. So to get a better idea if there is an increase in biomass, we need to look at the depth integrated chlorophyll fluorescence, which is in the bottom graph. And here we can see that during all these pulses, we do get an increase in depth integrated chlorophyll. So this is even more evidence to suggest that there is active growth going on in these pulses, specifically this one here, which is the main event. Why is this important? Well, phytoplankton have a species succession. You generally have larger cells during the earlier months, particularly at the beginning of the spring bloom, and then you gradually go down to very small cells. And each of these different phytoplankton species have different nutrient requirements, and they also contribute differently. Contribute differently to different amounts of carbon sequestration. So really knowing exactly what phytoplankton species are in which blob and how that would affect the succession is really important in knowing the grand scheme of things. It could be that the phytoplankton species in here is different to here and would ultimately affect the rest of the spring bloom and also the subsurface chlorophyll maximum in summer as well. So again, I'll be using models to have a look at this and to model the seasonal phytoplankton succession based on earlier stratification and based off rainfall stratification as well. So to conclude, we can see that during most winter months, we see a daily cycle of heating and cooling that results in daytime stratification, but then nighttime convection. But there was a period of heavy rainfall on the 25th of March that was responsible for a period of halo stratification and actually lasted about 4 days. And this increases surface buoyancy. This increases surface buoyancy. So we did get this sustained stratification, and actually triggered seasonal stratification in the Celtic Sea. So I'll be using more models to test both the biophysical interactions at a more community level state. So thank you.